with what I ended on last time. Well, last time we talked, or yesterday we talked about which series obey Color-Kinematics Duality, and then we in that discussion we also talked about double copies, but I want to give a little bit more on the double copy details. Obviously, there's lots of things that can be said, and I'm not going to be very systematic in what I'm going to cover, but let's say a little bit more about it. And then after I've done that, I'm actually going to connect to what David talked about this morning, which was this massive spinners. And so I'm going to discuss how that connects to rotating black holes or spinning black holes. And there's also a double copy story there, so that's why I need to fit it in here. But okay, so let's talk about some double copy theories. And here I'm not going to be very systematic, as I said. So let's just going to give a few examples. So for example, assume that you have some supersymmetry. So then we have, let's say we have, it's going to look a bit weird, but let's say the number of supersymmetries is p. So we take this one to be our super Yang-Mills, and then we double copy with something which has n equals to q supersymmetries. And this is then going to give us some supergravity where the number of supersymmetries add up. So basically P plus Q supergravity. And of course, it's a little bit more tricky. You have to think about which dimension you're in and so on. And if you have a chiral, supersymmetry and whatever. But roughly, this is how it works. And I'm not going to say much more than that. If you have any questions about this supergravities, let me know. Yeah, otherwise, I mean, I guess we already talked about that, but let me remind you. So if you take this Yang-Mills scalar, well, it's a scalar, and you double copy that with Yang-Mills, what you get is essentially GR plus Maxwell. Especially if you have, well, if you have a single scalar, then you get a single Maxwell field and so on. And if you take this Yang-Mills and the Bayer joint, which I often call just phi cube, then times Yang-Mills, then you get GR plus Yang-Mills, which I guess we called Einstein Yang-Mills last time. And I guess you can call this thing, some people call it Einstein-Maxwell or Maxwell-Einstein. I guess there's a disagreement of which one goes first. Then people like to make this multiplication table, so let me do that. So if we have Yang-Mills on this column here, we have Yang-Mills scalar. I guess this is the Yang-Mills scalar. Well, either of them is Yang-Mills scalar, I guess. And then, let's see where they go. We can put the nonlinear sigma model. And lastly, just put the bijoint scalar. And then we can also put the same thing over here. Yang-Mills scalar, nonlinear sigma model, and bijoint scalar. Okay, so then we can start filling out the entries here. What do you get when you double copy this series? So as we already said, this is GR plus maybe some extra fields, some extra matter. Here, as I already discussed, is Einstein-Maxwell or Einstein-Yang-Mills, depending if it's abelian or non-abelian, or whether which one of those Yang-Mills scalar theory it is. Here you get actually what's known as Born-Infeld. which I will come to shortly, but let me just name drop it there. Here, well, let me do this one. So this obviously is just going to be Yang-Mills because, as I said before, this Bayesian scalar just acts like identity multiplication by identity. On this multiplication table is symmetric, so I only need to fill out part of it. So here you get Einstein Maxwell plus the scalar, or Einstein Yang-Mills plus scalar, and you can work out the details yourself. Here you get what people usually call DBI, so Dirac-Born-Infeld. Maybe I didn't say this is Born-Infeld. Here you get something that people call special Galilean. Let me write it like this. Which I'm not going to explain what it is, but it's well known. And as I said before, this just acts as identity. You get only a sigma-mole here, and by a joint scalar. Okay, good. So maybe I should say something about Born-Infeld, just so for those who don't know. So the Born-Infeld is actually a nonlinear version of electrodynamics. So you can write the Lagrangian as follows. Essentially, it's a square root of a determinant. Let me do it below here. So it's a square root of a determinant, and then it's basically eta mu nu plus alpha f mu nu. Sometimes there's some factors of pi, but I don't really care about those. So this is a nonlinear version of Maxwell. So you can expand it out. The first term is just going to be the Maxwell, whereas then you have higher order, to all infinite orders powers in the field strength. And what is dBi? Well, dBi is pretty much the same, except that now you include some scalars in your story, which you can actually just get from dimensional compactification of the Born-Infeld. So it's not much difference between those two series. All right. Any questions about that? Yeah. Sorry, I could not hear. Can you say it again? Yeah.
So for the first case, let's say we take n equals 2 super Yang-Mills and n equals 2 super Yang-Mills.
Yeah.
And in the second case, we take n equals 4 and n equals 0.
Yeah.
Will the double copy be exactly same?
Oh, you mean when there's an ambiguity?
Yeah.
Yes, right. You can write, I forget which one you said, 4 is equal to 2 plus 2, or 4 is equal to 4 plus 0. Yes, yes. that's two ways to get 4. Yes, so they typically give the same thing, but the matter can be different. So there's always a little bit of matter. Well, not always, but in this case, you're going to get some extra matter, which you're not going to have here. So this is going to give you pure n equals 4 supergravity, and this is going to give you n equals 4 supergravity with some extra multiplets. But there is, as I said, we have this prescription for removing this extra multiplets, which you can just do using super QCD in this case. And then if you remove it, they give actually the same thing, yeah. But they're realizing it in a very different way, so it's kind of interesting, yeah.
Thank you.
Yep. Well, it's not so, well, I think once you get the hang of it, it's easy to see. It's essentially, yeah, how to think about it. Typically, when you split the supersymmetry like this, you get matter, whereas if you put all of it on one side, you don't, yeah. Yeah. But it's a very good question, but yeah, I think it's easiest if you just figure it out yourself. Yeah, because otherwise, otherwise just have to trust me. Yeah. You can just multiply the spectrum and just count. You know, it's just a counting game, I guess. Yeah. But yeah, there is also, once you have done it enough number of times, you kind of recognize the pattern, I guess. Yeah. Okay, good. Then the last thing I was going to say about the double copy is also a multiplication table, but in this case, it's going to be some stringy object. String object times a QFT object. So it looks a bit weird, but let's do it. Maybe I should have made it bigger. Let's make it a bit bigger. Let's do it over here. So let's put super Yang Mills here. Let's put, I haven't explained this theory, but let's put it anyhow here. I will explain it shortly, I guess. Okay, so I put 3 QFTs so far, and I will put some stringy objects soon, but let's just explain this QFT. So this is just super Yang Mills, which you can take to be the maximally supersymmetric. Either in 4 dimensions it would be n equals 4, or if you're in 10 dimensions, it would just be the n equals 1 in 10D. Let me just put 10D, so we stick to the string way of doing things. And what is this? Well, this is just pure Yang Mills, but now you have sort of coupled it to a higher derivative coupling. And this is actually just shorthand for actually a pretty ugly Lagrangian. So there's actually an ugly Lagrangian that we call df square. So I'm not going to try to explain it, but it has a bunch of terms. It has f cube. It has some extra matter, but I'm not going to explain what it is. You can ask me maybe privately. And here you're basically taking the Yang Mills and phi cube, which we talked about over there, but now you have also deformed it by this higher derivative stuff. Also, Thales is one of the experts who was in the paper that worked at the table I'm going to write down now, so you can ask him about the details. Okay, so here I put this Z theory that I talked about yesterday, which was just some stringy disk amplitude that doesn't really have some interpretation as a straightforward string, but it is definitely stringy. It depends on alpha prime, and it was useful for getting the superstring amplitude once you double copy with super Yang Mills. So that's actually the first enter here. So open superstring. All right, so, okay. And if you double copy Z theory with this guy here, then what you get is actually open bosonic string. Well, yeah, it's fine. And if you do it with this guy here, what you actually end up getting is, well, let me actually leave that entry for later. So now I'm going to introduce another stringy object. And this is what people, I'm actually going to put the open superstring here as well. But I'm going to apply an operation to it that people call single value. Essentially, what this single value projection does for you is that it turns objects which look open into something that looks more closed, I guess, meaning that this super amplitude has some multi-valuedness about it because it's living on the boundary of the disk. But then you apply the single value projection, which is a mathematical operation, and they look more closed. I'm not going to explain it here. There is a formula for it. But anyhow, so when you double copy that with superyang mills, you get the closed superstring. And here you get heterotic superstring. Well, I guess it's always superstring. But only the gravitational sector of it. Meaning that it's only external gravitons. However, if you do it here, what you get is heterotic superstring. But now you get gravitons and gluons.
Henrik.
So now you get both the gauge boson and the gravitons. Yep.
So in the gravitational sector, does it have a higher derivative as well in the heterotic case?
It's just it's the full tree level or full sphere amplitude, but you just restrict the external states to be only gravitons. That's what it is. Yeah. So it has everything, like everything that the string has, but you restrict to external gravitons which are massless. But internally, everything is propagating. Yeah. So all the higher derivatives are yeah. And this is tree level or disk level, so tree level. The loop level generalization is, I guess, open for research. Okay, I guess I had one more. Row here, which is also you can also put the open bosonic string. String, and also apply the single value projection. And then what you get here is that you actually get the same. You get the same here. So I'm not going to write it down. Here you get the closed bosonic string. And okay, so I didn't say what you're getting here. So what you get here is you get compactified open bosonic string. And likewise here you get compactified closed bosonic string. Sorry for my handwriting. So you can just think of that as some, well, any kind of compactification, but in particular, the easy ones are on a torus, I suppose. And of course, it's well known that the heterotic string, the gluons and the heterotic string are in fact from compactification of the bosonic sector. So you compactify from 26 dimension down to 10 dimension, and that's how these gluons appear. So it makes sense that in this column we have some theories which are compactifying. All right, so I'm just flashing this in front of you. I'm not really explaining it, but you know, if you have questions, ask Thales or somebody else. And essentially all of the tree-level string amplitudes are here, maybe with one exception. And the one exception would maybe be that if you scatter open string and closed string at the same time, then this is not here. But on the other hand, people usually think of that as not being tree level. Usually people think of that as being a loop correction. So basically, yeah, simplest example, if you have like an annulus, and the hole in the annulus is just interpreted as a closed string. Sorry, as an open, sorry, now I'm saying it wrong. I think it's correct, yeah. So the annulus is a closed string. We can just stretch it out, it becomes a closed string. So this is not here, but that's on the other end. It's not exactly tree level. All right, any questions before I switch topic? All right, so what I want to talk about next, I want to talk about, I want basically continue where David ended in his talk and talk about some massive spinning amplitudes and whether there's a double copy story there as well, and the answer is yes, but mainly for low spins. Okay. I was also planning to talk about the classical double copy, but I did that in a colloquium, so I feel like I don't need to repeat it because it's not going to be much deeper than I said there. So let's talk about like a Kerr black hole at 3 points. And spin. And I should say that this is actually, well, it's going to overlap with what David talked about. So in particular, it's going to involve this paper by Khan Mohammed and Huang. And then there's also some reference. So let me put another reference here, which is Vines from 2017. And then there was work by Alfredo. So this is celebrated GOV. It's a very nice GOV paper. And there's another paper by the same authors that was mentioned in David's talk. So CHKL, I guess. So that's the paper that was mentioned in David's talk. So I'm not going to write it out. So this is that guy over there. All right, so what Khan Mohammed and Huang did, of course, is that they wrote down this very nice formula for 3-point scattering between two equal mass and equal spin objects, and then a graviton. So let me write it like that. I think I'm using the same notation as David did. And then you can write that. And now, yeah, I could introduce the X factor, but let me, for simplicity, actually just write it like this: 1, 2, like this. 1, 2, 2s over m2s. So this is basically the same amplitude, but for 0 spin. And you can also write that as this x squared, I believe. Usually people write it as x squared in the case of gravity. You can also write it just as a 3-point amplitude in covariant notation. So that would be P1 minus P2 dot epsilon 3 plus, and then you square this thing. Yeah, and that explains why this X factor has some dependence on a reference momenta, because usually our polarization has a reference momenta. Okay, so this is that. Okay, good. And then what Alfredo and friends really nicely showed in this paper and also in that paper was that this amplitude can be secretly rewritten as and I have to apologize to Alfredo. I'm not going to use your notation, so I'll use my own notation. So basically, P3 mu S mu over m. So you can rewrite it like this. If you take h bar to 0, so basically a classical limit. In the classical limit, you get an exponential. This thing here is a spin vector, which is a classical object. This is just the momenta of the graviton. So in fact, this formula I think was known before Alfredo's work, and I think it was first given in this paper by Justin Vines. But he actually computed it from GR directly, and he also wrote it in different notation than what I wrote here. But it was known that you can compute a 3-point amplitude in a classical theory that has an exponential of this spin vector. And now you can now expand this out, and then you get the spin multiples corresponding to this process. And you can also clean this up. So sometimes people just write it as E, then Q dot A, where well, Q is just the same as P3 in this case, and A is just the same as S mu over M. And this is also known as the ring radius vector. It's essentially, if you have this Kerr black hole, it has a ring singularity. The ring singularity has a radius A, and it has a direction, so that's the ring radius vector. Okay. Yes, so what I wanted to show here is two things. So one thing is how do you go from here to there? And the other thing I want to show is that there is some double copy structure here that seems to continue, but mainly for low spin. But that's the plan of the rest of this lecture. Any questions so far? No. Yes, so first of all, I need to define my variables a little bit, just like in David's talk. So essentially, I'm using the same notation as David, but it's very convenient to get rid of this little group indices, the SU2 little group indices. So if I have this spinner with a little group index I, it's very convenient to just get rid of it by contracting with an auxiliary variables. So essentially, I'm always going to take that to be my massive momenta. And if I follow David's notation, I guess I should put an underscore to indicate that it's massive. But I will often forget that probably. But so that's my definition of the spinners that I plug in here. And the reason why that's useful is because it will automatically symmetrize over the little group. So there was a question at the end of David's talk, how do you symmetrize? Well, this is one way of doing it. You just multiply by an auxiliary variable. Now it will always be symmetric. And the reason why it always be symmetric is that if you actually want access to the indices that you have, I mean, if you want to undo this contracting in, the undoing is actually taking a derivative, right? So pi is d zi of this spinner, right? So in order to get out the index again, you have to take a derivative, and the derivative will always symmetrize, right? So everything is guaranteed to be symmetric. But there's also another reason why this variable is important, is because it actually has a physical interpretation. And that's essentially that it's actually the wave function for the quantum mechanical spin. So you might recall that in quantum mechanics, we say that, well, you know, an object can either be spin up or it can be spin down. And I apologize for using Ketz for two different purposes. This is not a spinner. This is just a quantum mechanical state. This is a quantum mechanical state up. This is a quantum mechanical state down. And in fact, the coefficients here are just this Z1 and Z2. So this will be useful when you talk about the classical spin, because you can't assign a little group index for classical spin, right? You just have to say it's a vector. So you basically have to use this wave function to get from the little group indices to something which do not have little group indices. Also, I should say that only today did I realize that also this paper did the same trick, but they only did an appendix, which nobody reads. So I only realized it today. But I picked the letter T. I think the reason why we picked Z is because it has to do with the spin quantization axis, and that's usually in the Z direction. So that's sort of the reason why we picked Z. Okay. Any questions on that? Okay. So now the key step from going from here to there is that we have to realize that this 1, 2 to the power 2s, which according to my definition now is like 1 I 2 j, where we contract this, we contract j and we contract z I here, and then we take power 2s. Although here I did an error. I don't know if you noticed I did an error. The error I did is that I used the same z for two different particles. Obviously, they have different little group, so they should have different z's. So I can just fix that by putting a bar here. Well, actually, maybe I should. Yeah, let's put it here instead. Let's put it there. Whatever. So one of them goes with particle 2, the other one goes with particle 1, and I put a bar to distinguish them. And you can, if you want, you can actually think of that as complex conjugation, because I only have two particles, so you might as well put them in the same complex variable. Okay. And then the question is, can we now relate this to some function that depends on the spin vector? So for now, I mean, of course, we know that the function is going to be an exponential, but let's assume it's a generic function. And furthermore, I actually want to make it a function of the spin operator, quantum mechanical spin operator. But of course, it's really a classical object, so then I have to take the expectation value of that operator. So that's basically what I want to do. I want to go from there to here. And you can kind of see that this expectation value might have something to do with those guys. That's not coincident. Okay. Okay, and what is this spin operator? So the spin operator is the Pauli. It's basically the Pauli-Lubansky pseudovector. So I put the hat to remind ourselves that it's actually not a vector, but it's an operator. But well, it's also a vector, I guess. But okay, so that's the Pauli-Lubansky pseudovector. Basically, just a momenta, and then the Lorentz generators, and then you contract the Vilevich-Civita. And m here is just the mass of the objects. Particle 1 and particle 2 have the same mass, but which momenta should I use? Well, it turns out that in classical limit it doesn't really matter, but to be careful, let's make it momentum 1. So particle 1 is the one we associate this guy with. So this is actually the spin operator that we want to act then on particle 1. Okay, and so the question is, what is this object? What is the expectation value of this object? Well, it's actually just this thing sandwiched between the brass and kets of our one particle state. So it's just this thing here to the power 2s, this one also to the power 2s. And also what I should do here, I should put a ket and a bra, and I should interpret it basically as, well, one of them incoming, one outgoing. I actually need to put a bar here. I will explain the bar later on. But that's essentially, it's just a quantum mechanical expectation value of this state. So that almost looks like what we have, except that we have a 2 there, right? Oh, actually, maybe I should put the bar over here. Let's put it there. So we have a 2. So how do we go from particle 2 to particle 1? Well, it turns out we can go from particle 2 to particle 1 by a boost. So a Lorentz boost. So basically we want to go from, well, so here, so spinner 2. So this is just a kinematic identity, essentially, that I can write it as spinner 1. Well, I can write it as a boost applied, basically e to the lambda 1/2, I guess. I'm being a bit sloppy here, but you can always write as a, well, sorry, not lambda. So the Lorentz boost for spin 1/2 representation acting on spinner 1. And it actually has a really simple formula, so let me just write it. Sorry, acting on, sorry, what is it do I want here? Sorry, I think I screwed up. Let's take a step back. The point is that it's a boost, so let me just write down the formula instead of trying to write some intermediate steps. Okay, so it doesn't look like a boost because it's linear. It's obviously linear in the, you can think of this as the boost parameter. This is just the Pauli matrix dotted into momentum 3. This Pauli matrix acts on the spinner. So it doesn't look like a boost, but the reason for that is because the kinematics and the spin is so simple that the exponentiated boost operator just becomes a linear transformation, essentially. So essentially what we have done here is that we have shown that the ket for particle 2 is a linear combination of the kets and the angle ket and the square ket for particle 1. So this is just a change of variables. That's the one way to think of it. Okay, so now we can plug this formula in here and work out what we get. So basically, if we just take 1 power to begin with, so 1 power of this 1, 2, so it's essentially 1 and 1 bar plus 1, 2 over 2m, and then 1 and 1 bar, sorry, sigma mu, 1 bar, and then p 3 mu. Okay, there we go. Okay, so now okay, maybe I should explain what this bar means here. This means that this is actually the dual. It's basically the dual state of that one. So that means that this thing here is 1. So if I hadn't put the bar, you probably realize that this thing is 0. But this is the dualized. So another way I can say that 1 is equal to 1 I, Zi, whereas 1 bar is equal to 1 I and then Z bar. So basically just complex conjugate this variable. That's what I mean by that notation. And now you see that if I normalize my Z to be 1, then I get the 1 there. So it's just a normalization of the wave function, of the spin wave function. Okay, good. So we're not yet where we want to be. So we need to work a bit harder. So essentially what we need to do is now we need to take this power. So 1, 2 to the power 2s. And then obviously what we're going to get here, we're going to get something very ugly. If we expand out this expression, I can already do it here, right? If I, sorry, not 2s. If we expand this out, it's going to be something very ugly. But we can use the binomial expansion formula, right? So in fact, this is a binomial expansion. And now also you can well, it's not obvious here, but this is actually the expectation value. So let me actually write that right away. Yeah, maybe I should clarify that. Yeah, you can work out that this thing here is in fact this thing here. So it is the expectation value of the Pauli-Lobansky operator. It doesn't quite look so, also because there's a square bracket here. But trust me, if you just plug that in and work a bit, you will realize that these two things are equal. So we can just use this object. So basically, this to the power k, and then we have some binomial coefficients. Okay, so that's just a binomial expansion of 1 plus this guy, right? And this is actually spin 1/2 representation. That's what I was trying to indicate there. Because you have to decide in which representation you're working in. And obviously we're working in the 1/2 representation because we're applying it to spinners. Okay. Okay, and now we are going to use some magic. So the magic we're going to use is that you can actually change representations. So if I want to go to the spin S representation, there's a formula. And I can do it for an arbitrary power k. So there's a formula which looks like this, 2s factorial over 2s minus k factorial, and then s 1/2 mu to the power k. Right. So basically, if I have a spin 1/2 operator, I can trade it for to some power. I can trade it for an operator in the spin S representation, but I have to multiply and divide by some factorial terms. And I should say there's also corrections here, but all of those corrections turn out to be proportional to P1. And so they won't be relevant because in the end of the day, I'm going to take a dot product here with P3. And therefore, the dot product is actually going to be orthogonal, as David explained. The P1 dot P3 is actually 0. Okay, so if I use this formula, so this is just a comment. So if I use that formula in here, then you can show that, well, actually lots of these guys cancel. Well, it doesn't look like it cancels, but I guess I wrote it the other way around. So if you put this on the other side, then it will cancel here. So essentially, what I have written here is this thing. So so basically sum over k from 0 to 2s. The s operator in the s representation now dot p3 over m over 1 over k factorials. So the k factorial remains. And in fact, now I can just put the expectation value on the outside, because this is an equation at the operator level. And you see that this is actually an exponential. Yeah, this board is not so good, so apologies for that. All right, do you agree? Or did I do a mistake? You might argue that, well, this is not an exponential, it's a truncated exponential. But it's not true, it is an exponential. It turns out that when you take more than 2s powers of this guy, it will go to 0. So this operator is actually nilpotent. I mean, after taking 2s powers, it goes to 0. So in fact, this is exact. That at no step in this derivation was there any approximation. It's an exact formula in the quantum case. But now we want to take the classical limit. So we want to take now h bar goes to 0. However, taking h bar goes to 0 is not sufficient to do classical physics. We also have to take s to infinity. Because we want to have the product of s and h has to be finite. Because classically we measure angular momentum as the quantum s times h bar, right? So both of them has to go to some limit and have to go to the limit simultaneously. Yeah, so that's what you want to do. And this can actually be implemented without actually doing anything, because we know that in the classical case, we know that if you take the square of an expectation value, it's actually the same as taking the square of the operator and then taking the expectation value. This means that the difference of these two guys is 0. The difference is the variance. So the variance is 0 in classical limit. So therefore, this thing here actually just becomes e to the expectation value of s dot p3. And now we can just define this thing to be our classical spin vector. Yeah, and we can also write it in terms of this a dot p3. Anyhow, so that was a long derivation, but I think the cool part is that it's actually not that hard to do it if you actually do it yourself. Looks like a mess here, but and the cool thing is that you can keep it exact all the way to the end, and that's where you take the classical limit. Then I should also say that, oh yeah, so you might wonder, why did I talk about taking s to infinity here? I think in many cases people don't bother about doing that, especially at 3-point level. I think the only implication here is maybe that I had to change the spin s representation such that I'm talking about the actual representation of the object that I'm interested in. But then, of course, when I take s to infinity here, I just reinterpret this thing as being the classical spin. So it doesn't have much of a consequence. Let's see, how am I doing in time? Plenty? Yeah. Okay, so having shown that, then I wanted to talk about which theories are actually in this amplitude, the amplitudes that David talked about this morning, and there's one for the square bracket as well. What theories are they? So we know a little bit about those theories. We know what they are at low spin. We don't really know what they are at higher spin. We only know bits and pieces. So what effective theories, so EFTs, give this Kerr, let's call it the Kerr 3-point amplitude, or although maybe I'm stretching that word a bit. Or you can also call it the AHH 3-point amplitude. By the way, this 3-point amplitude uses complex kinematics. I'm not sure if David explained that, but the kinematics is a bit degenerate. So it's not really possible to compare to GR except for in the soft limit. And the soft limit you can compare to the source, stress energy tensor source of a rotating black hole, and that's what Vines did in 2017. Okay, so let's actually start from the non-spinning case. So this is actually the Schwarzschild case. So spin 0. So that would be Schwarzschild. Let's see if I get the spelling correct. So then it's well known that if you just start from a minimally coupled scalar, it does a very good job. So basically, plus, I guess it's a mass term as well. I hope I got the sign right. Okay, so this one does a really good job. And let's try to show that. So what we can do is we can extract the 3-point vertex from this Lagrangian. Obviously, this is coupled to GR, but I don't write out the Einstein-Hilbert term. But here you have to use the metric here. So let's just look at the term which is linear in the metric. Well, so there's one term coming from here that's linear in metric. But let's forget about that one because it's not going to contribute on shell. So we only need to work out the linear coupling here. And that's of course very easy. So this is just going to be d mu phi, d nu phi, and then h mu nu. And here I'm lowering and erasing. We have to eat that as the flat metric. That's fine. So this is basically the coupling. Maybe the 1/2 is still there. And maybe there's a kappa, but let's forget about the kappa. So all I need to do is I need to work out my amplitude from this interaction. And I think it's not very hard to realize that the amplitude is, so let's say plus minus. So it's, well, let's put the kappa for good measure, kappa. So this is going to be kappa P1 dot epsilon 3 plus minus squared. So essentially what I've done here is I just replaced this by epsilon mu, epsilon nu, and then you see that epsilon is dotted into the momenta. And well, one of them is actually dotted into the momenta of particle 1 and the other one particle 2, but of course it's going to actually be the same when I use integration by parts. So maybe there's a minus sign because of that. Well, there's also a minus sign because of the going from derivative to momenta. Anyhow, so that is this is actually x, this thing here, x, or x plus minus 1. And you square this x to get this 3-point amplitude. So that explains why that amplitude looks the way it looks. It's just a minimally coupled scalar. I'm not claiming that that's the full Lagrangian through all loops or whatever, but it's the Lagrangian that works for the purposes that people have studied so far. Okay, what about spin 1/2? So that we can actually think of as an electron in GR. So just couple an electron to GR. So let's call the electron wave function psi. And then I have the covariant derivative here, slash. Right, that's the direct Lagrangian, but now I have included a metric in it. And also now we want to expand this as well to linear order in the metric. And again, we can actually forget about the square root of g because it won't contribute on shell. So basically what this is going to give us is going to be, if I expand it out, minus I over 2 yes, plus I over 8 psi gamma mu omega mu a b. Okay, gamma b psi. Okay, it looks like a mess. So here the metric perturbation h appears, and you might wonder what the heck does this notation mean? Well, it means that I have put in a gamma matrix in one of the indices of h, and then the other index of h I've dotted into this derivative. So this derivative is not slashed, only h is slashed. And this omega here is actually the spin connection. The spin connection, you can actually approximate, like for this linearized field, you can approximate it to be equal to, or at least on shell, it will be equal to epsilon mu, and then PA epsilon B antisymmetric. That's just a polarization. That's just a momenta. But that's what it becomes after you have done, the Fourier transform and all of that. But it turns out that all of this term is actually 0 on shell, so we don't care about it. And the only term that we need is actually this one, because that's just a kinetic term, of course, but this is the interaction term. So that gives the whole answer. So therefore, m of 1/2 spin particles is actually equal to 1/2 epsilon 3 dot p1, and then due to epsilon 3 nu 1. And these are just solutions to the Dirac equation, the u and the v spinners. This guy here just came from this dot product here. This thing here is just the on-shell wave function of these two guys. Anyhow, and now you see that that's actually there's two factors here. So in fact, this is actually a double copy There's also kappa, which I forget somewhere. So this is a double copy of spin 0 and spin 1/2 gauge theory amplitudes. So this is scalar QED. And this is actual QED. You can say this is actually the same amplitude as in QCD, because at this level, this amplitude do not differ. Okay. And I'm not gonna do the next step, but if you actually plug in the massive spinners that David was talking about, it is gonna be 1, 2, 1, 2, or 1, 2 in the two different. So this is gonna be epsilon plus dot p squared, and this is gonna be epsilon minus p squared. Yeah, that you have to work out yourself, but it kind of looks like it's gonna work, right? Yep. This one here. I guess you have to. Yeah, I forget what the argument is. I think it should be 0 by the Dirac equation, I think. So you have a p here. Oh, sorry, this is the p of the graviton, though. So never mind. I forget. I leave it as a homework. Check that this is 0. Yeah, it's just 0 because of the on-shellness condition that we're using for this kinematics. Yeah. Yeah, maybe that's what it is. Gamma trace. Well, I mean, it's spin 1/2. They're automatically gamma traceless. Yeah. I think if you just plug in here and manipulate, it should be 0, I guess. But I don't see it right now. Okay, how much? I have 25 minutes left? Yeah. Okay. Okay, so I think I'm going to do one more example. And that's the Procca theory, which we already talked about, I think, last time. So that's spin 1, which is Procca. So I don't know if you remember your Procca action, but here it is, or Lagrangian, I guess. So it's basically just a massive photon. That's what it is. Just add the mass term. You might object that doesn't look very gauge invariant. It doesn't matter. It is. It's just a gauge fixed version of a gauge invariant action for U1. Here it's important to remember that the field strength is something like covariant derivative of A, something like that. Antisymmetrized maybe a factor 2 for good measure. And the covariant derivative is minus gamma mu nu rho A rho. Okay. So to linear order, in H, what you get is that gamma, the Christoffel symbol is basically also a combination of momenta and H, I guess. I guess symmetrize here, and then I subtract. And I think there's a factor 1/2, I think. And I could also plug in the polarization vectors here. So that's the contribution of H coming from here. There's also a contribution just from the contraction of two field strengths, because there is a F mu nu, F rho sigma. Well, let me contract mu nu rho H nu rho. So there's a linear term in H that's contracted with this field strengths. Anyhow, it's slightly more messy, but you can work out the detail, and you get that the spin 1, massive spin 1, interacting with a graviton is going to be epsilon 3 dot p1, and then epsilon 1 dot p2, and then p1 minus p2, epsilon 3 plus cyclic. And you might recognize that's just actually just Yang-Mills. This is just Yang-Mills vertex. And this is scalar QED, just as before. You might be surprised that Yang-Mills vertex showed up here with scattering massive particles. Why did the Yang-Mills vertex show up? Well, it turns out that if you have massive W bosons or massless gluons, the Yang-Mills vertex stays the same. So you can, in fact, you can even think of this as being spontaneously broken. Sorry, SSB. So spontaneously broken Yang-Mills vertex is the same as a regular Yang-Mills vertex. And then the last step, which I'm not going to show here, but the last step, of course, is that you get this 1-2 factor to the power 2, or you get the 1-2 factor to the power 2 in the two different helicity sector, and that's also the X factor in front there, which I'm not displaying. But it's a useful exercise to work out this from this Lagrangian, and then it's a second useful exercise to show that this covariant expression here can be written in terms of this spinners. So that's the homework, I guess. I guess in general, all of these calculations that I'm doing here, I think you should just do them yourself. It's very useful. You know, once you have done this, you know how perturbation theory works in DR. Okay, any questions? All right, so I'm not going to do any higher spin. You're not going to see me suffer through spin 3/2. But you can do spin 3/2, and it will work out. It will recover this 3-point amplitude that Akane-Hamed, Huang, and Huang wrote down. You can also do Fierce-Pauli. Fierce-Pauli is the action for massive spin 2. Although you have to be a bit careful how you covariantize Fierce-Pauli. But I'm not going to show it here. So maybe I should say something about the Compton amplitude. So David already derived one of the Compton amplitude. So let me write the one that he derived. So Compton I think David. I think you were doing gravity, I guess. So hopefully I'm gonna write down the same formula as you did, but I might have picked different conventions for which particle is which. Let's put a 1 here. It's just 1. Well, he might be listening secretly. Okay. So that's, I think he wrote that slightly different. This is basically this spurious pole issue. And then we had just the Mandelstams downstairs. And I'm pretty sure I must have picked some other Mandelstams that are massive than what David picked. I think that's what he picked, but anyhow. Same. Oh, okay. Anyhow, it's all the same up to some permutation and relabeling, I guess, yeah. Okay, and so the issue here, as David pointed out, is that this is actually a spurious pole for S larger than 2. And I should say that there's an equivalent expression. So if we call this kerr, which maybe is a stretch, but let's call it kerr, then there's a corresponding root kerr, which is a gauge theory object. Which almost looks the same. But it's 2 minus 2s here. This power is actually the same. And the denominator is different because you have to decide which color ordering you're doing. So if we just do the standard one, which is usually S and T, then I get this one. You can also do it. You can also do the case where you have only the massive poles, and that would actually correspond to massive electrodynamics. But now, obviously, this, because it has a massive pole, this also has a gluon. So this is actually massive QED, I guess. QCD, sorry, massive QCD. Yep. Say again? Different to list this? Yes, thanks. Yes, it's because my notes, I decided to write the amplitudes in a different order than in my notes. So this also has a spurious pole. For S larger than 1. Actually, spurious pole is maybe bad terminology, but everybody calls it that. Usually, spurious poles means that it's a pole that vanishes. You know, cancel here. It does not vanish. This pole is actually there, but it shouldn't be there. That's the point. So, in a correct theory, you shouldn't be able to have such poles. And as David said, removing the pole is actually not that hard. It was done already in 2018 in this paper. That said, after you have removed the pole, there's still an ambiguity in that you can add gauge invariant contact terms, and fixing them, that's a whole different story, which I'm not going to talk about here. But that's basically the main crux in trying to continue the series beyond this spin and beyond that spin. You have to be careful about these extra contact terms, which nobody really knows what they are. But the point is that there are nice formulas, and in fact, I can even write down another nice formula, which is in this other helicity sector. So if you do same helicity, sorry. So if both graviton are plus helicity, then you get actually an even nicer formula. M2s minus 4, I think. S T minus m squared u minus m squared. Okay. And so this actually has no spurious pole. No spurious pole. And there's a similar one for A. It's exactly the same, except that you have, except that this thing is a 2 instead, and then you cross out one of these guys. That would give you the gauge theory one. Okay, so oh, by the way, so this were worked out in a Color-Kinematics Huang and Huang paper by I think they just used factorization, which is essentially what David used also this morning. But you can also just use BCFW, and you get these formulas. I'm not sure if you can get more than one formula depending on which shift you're doing. I think you get the same regardless of which shift. This was not worked out in our Hamed and Huang paper. I don't know why they didn't give it. So this was given in a later paper by me and Alex Oshirov. We also use BCFW, I guess. Yeah, so now what we want to do is actually, we want to take the classical limit of these objects, and I'm just going to do it very quickly, and just do it over here. Well, maybe over there as well. So let's take the classical limit. H bar goes to 0. S goes to infinity. I'm not going to show you the details, but the expression that you get is you get the non-spinning amplitude. So that's S equals to 0, or also in the gauge theory one, S equals to 0. So choose which one you like, gauge theory or gravity. And then you get E to the A dot P3. Let's see, what is it? P4 minus P3, I think. Plus, and then you get 3A4 3 1 4, and then P dot Q4 minus Q3. Yeah, it's not obvious. All of this is sitting in the exponent. So let's write a big exponent. Okay. And so you can see that after taking the classical limit, you get something which is fairly nice. This guy is nice. This one is less nice because you see the spurious pole and the exponent. That said, it's not so bad as it looks here. It looks bad, but it's not so bad because you can actually expand out this term to a few orders. And to a few orders, this pole here will actually cancel against 4 positive powers. So there's 4 positive powers here, this powers here. So you can actually expand it to 4th order and it's still fine. For the gauge theory one, you can only expand it to 2nd order. After that, this spurious pole is a real issue, right? Yeah, so the problem remains even after having taken the classical limit. You can do the same thing here, take the classical limit, and you actually get exactly the same formula as you have. I guess I have erased it. You get pretty much the same formula as a 3-point. So this was minus plus. So here you get M plus plus, A plus plus, and you get E to the A dot P3 plus P4. And this thing here you can also call Q, and then it's exactly the same thing as the 3-point. Is the sky falling apart? Yes. Yes. God is not happy. Uh, all right, so where are we? Okay, I guess I have a few more minutes. Yep. Oh yeah, that's right. Good, good. I was gonna say that. I was gonna say it. That's exactly why I show them. So indeed, this gravity amplitude here is the double copy of that one. Likewise, even though I didn't write out the details, but you can show that the gauge theory, if you double copy the gauge theory of yourself, you get this one. You might say, well, I'm anti-doubling up the spin when I'm double copy. Well, you have to just redefine the spin. You have to say, you know, I take half of the spin on one side and half of the spin of the other side. But the point is that double copy of this guy gives that guy, or if you wish, you can just plug it into KLT. So there's a KLT formula that takes you from here to there. So then, yeah, okay, so double copy seems really happy, but that's actually a false conclusion. And it's false because you still have the spurious pole, right? So you have to deal with the spurious pole. And it turns out that once you write down corrections for the spurious pole, it no longer satisfy the double copy starting at spin 2. So you can go up to spin 2 in gravity, and double copy is happy. But once you get to spin 5/2, their double copy does not quite work. And this might not be so well known in the literature, but it has been stated in the literature a couple of times. And this is irrespective of which contact terms you add. You know, as long as you get rid of the spurious pole, there's a small breaking of the double copy. Yeah, this one does, but on the other hand, it's kind of trivial. So yeah. So this one does, yeah. But you would want the whole theory to satisfy double copy, and obviously, if there's one sector that doesn't, then yeah. Yes, yes. Yeah, this is beautiful, yeah, and yes, right. Yeah. Also, this formula has a generalization for any number of gravitons. Basically, it looks the same. Whether or not that actually describes the black hole is maybe not proven, but it looks nice. It looks like there's a nice continuation of that formula. I don't know did you prove that it matches that self-dual black hole? Yeah, okay, good, yes. To any multiplicity, or? Oh, okay, yeah, okay. But yeah, so there's a conflict here between having nice formulas which obeys double copy and having spurious pole-free formula. So whenever you write down a spurious pole-free formula, it's much messier than these formulas. So you shouldn't take this formula too serious when you hit the spurious pole. But before that, you can take the theories serious. So let me actually now just finish by writing a table. And this is basically the conclusion of this lecture. Which EFTs are we talking about? Yeah. Sorry, the existence of a spurious pole. You mean Weinberg's theorem is that you cannot have massless higher spin particles? That yeah. Kind of, in some sense. I mean, if you note this formula has no mass in the denominator, but obviously, just for dimensional reasons, you need something downstairs such that dimensions are correct. And this spurious pole, that is actually the ones that gives the dimensions to be correct. In this formula, you have a mass here, so that's how you get the correct mass dependence. And you must have this mass dependence here. Well, you must have it for dimensional reasons, but this is also what disallows you from taking a massless limit, right? If this was not here, then you could take the massless limit, no problem, but it's here, so you cannot. And then I said, you know, this M here is basically related to the spurious pole, Or in another way of saying it, once you have cured the spurious pole, this term will turn into a factor m, m squared. So yeah, so it's kind of related, but in a convoluted way, I guess, yeah. Okay, so then let's answer the question, what EFTs describe Kerr? So let's make a table here. Sorry for my crooked line. So I want to put Kerr here, and then root Kerr. Yeah, by the way, I don't know if I said that, but the gauge theory one is usually called root Kerr. Okay, so let's start with spin 1/2. All right, well, let's start with spin 0, I guess. 0. So this is just scalar, of course. Minimally coupled scalar. Spin 1/2. So here, I would like to say that this is actually Dirac. I mean, it's a charged spinning particle, minimally coupled. Let's call it a Dirac fermion. Here, it doesn't actually have to be charged. You could make a charge, but as long as there's nothing that actually carries that close to the charge. But maybe it's even easier to make the Majorana. So then it's explicitly not charged. So minimally coupled Majorana, minimally coupled Dirac. And then, okay, so then we go to spin 1. So this is, as I said, Proca. Okay, maybe somebody can guess what should go here. What's your favorite massive spin 1 theory? What? QED. Is there a massive spin 1 particle? Is there a massive spin 1 particle in QED? Well, maybe there are, but they're non-perturbative. What's a massive spin 1 particle in the standard model? W, yeah, so let's put W boson. So you might know that the Proca action and the W boson action differ at the cubic level. And that's why I make the distinction here, that you really need a Proca. You really need a W boson here, because otherwise you don't get cubic interaction. Specifically, the term that you're going to miss is a minimal coupling of this form. So this coupling is needed, and this is not present in Proca. Okay? Yes? What? Yes. So if you double copy a W boson with a scalar, sorry, this one with this one, you get Proca. Yeah. Okay, so what about spin 3/2? Anybody want to guess what the theory? Just tell me the name of the particle. What? Yes, Rorita Swinger. Swinger. Do you know how to spell his name? And so you might know that Rorita Swinger is the minimally coupled spin 3/2 particle. Well, you have to, of course, couple it. Well, Rorita Swinger is a free particle, but then you couple it minimally to gravity. So that's what goes here. Anybody want to take a guess what goes here? Say again? You're talking about the double copy? Yeah, it's well, I'm not sure actually. But let's say it's not a Rorita Swinger that goes here. So do you know any other spin 3/2 theory, which is very famous? Yes, Gravitino. You might be surprised that the Gravitino goes with the gauge theory. This is a gauge theory. But you might remember that when you break supersymmetry, then you get massive gravitinos, and they couple to the graviphoton. So this couples to a graviphoton, and it gives exactly the right coupling. Okay, and then, okay, let's go to spin 2. And I should also point out that we're already in the territory where we have spurious poles, right? So this theory, even though it's a nice theory, it does give rise to spurious poles. And the reason why it gives rise to spurious pole is that you have decoupled gravity. You have a gravitino but no gravity, and that's forbidden. And that's the existence, that's the reason for the spurious pole. Well, it's not really the reason for the spurious pole, but it's the reason why there are ambiguities that you can add operators, new operators. Okay, spin 2. Anybody want to guess? I guess I already mentioned Fierce-Pauli, but I actually want to call it Kaluza-Klein. Kaluza-Klein graviton. Graviton. And the reason for that is that when you take the Fierce-Pauli free particle and you try to covariantize it, it's actually ambiguous how you covariantize it, because you can do integration by parts and then covariantize, and then you can and this leads to an ambiguity, which is essentially if we call a massive graviton H, there's an ambiguity of this form. HH and then Riemann tensor, which is exactly the same term as over here, right? And so if you don't covariatize the Fierce-Pauli in the right way, then you don't get this term. So if you take Fierce-Pauli paper and read their action verbatim, then it actually does not give the Kaluza-Klein. But if you do some shuffling around of the derivative using integration by parts, then you can get the Kaluza-Klein gravity action. So I rather call it this, even though in the literature you will see people use Fierce-Pauli, but I think this is a better way of describing it. It also tells you that you can always get it from double copy, as I talked about yesterday. All right, and then here, I don't know, this is just some higher spin theory. Also higher spin theory here. Yes. So let me end it here. So this is S larger than 2. Yeah. But the point is that there's this very famous series, interactions, which seems to do a very good job at describing a Kerr black hole, at least up to some finite spin. You might complain that finite spin is not the same thing as classical spin, because in fact we have to take spin to infinity, right? But that turns out to be this property called spin universality, which essentially implies that you can from spin 1/2 you can extract the spin dipole. From spin 1 you can extract the quadrupole, and from spin 3/2 you can extract the octupole, and likewise spin 2 you can extract. Now I have to ask, what's it called? What comes after octupole? I can never remember. Hexadecapole, yes. So it turns out that there's a recipe to go from the quantum spin to the multipole expansion. And this is usually referred to as spin universality. And to me, that's a miracle, because in general, I wouldn't have expected that. I mean, there are, for example, you can look at string theory. In string theory, there's no spin universality. So you have to take spin to infinity if you want to have classical strings. But here it seems to work. Somehow the Kerr actions and this action seems to be very special for some reason, which we haven't yet understood. But then we also know that everything goes haywire once you go above spin 2. So what I'm saying here, I think we should take with a grain of salt when it comes to higher than spin 2. Personally, I don't believe that we have spin universality beyond spin 2. So that's just a low spin property, but other people might disagree. All right, so I think I'm going to end there. So thank you for listening to me.
Questions, more questions and comments and criticisms?
In the stringy double copy,
Yeah.
so the low alpha prime to 0 limit of the Z theory gives the B adjoint
Yep.
trace phi cube. What about of the single value?
Same, because
It's the same again?
this single value operation only acts on the alpha prime corrections, actually. Yeah.
Okay.
Or it really acts on the pi's and the Riemann zetas and so on, but you know that those goes together with alpha prime. I guess,
Okay.
yeah.
In particular, I guess taking this alpha prime to 0 limit doesn't commute with this double copy then, right? Because you have double copy, you have maybe the open superstring equal to Z theory times superring Mills, and then there's also superring Mills times the single value, which gives closed superstring. But
Well, I think they should commute the two limits, yeah.
okay.
Maybe it's just my table was maybe a bit confusing.
Okay.
I mean, I could have made a bigger table which was less confusing. But
Okay, maybe I
yeah.
misunderstood something
Yeah.
then. Thank you very much.
Yeah.
I guess everybody's tired by now.
Yeah.
You! Okay.
No, I'm kidding.
What?
Yes, just to comment on this KK gravitons. Yeah, I think all of this story up to spin 2 is easily derived from just a forward graviton amplitude in 10 dimensions, whatever dimension you want, as long as you can compactify things. We checked this for the photons, but I think it's maybe you also checked for gravitons, but just take a 4-point graviton amplitude, and if you can take it and dimensionally reduce it, then you will get these very same spin amplitudes. So in that sense, they are there already. This one on the other hand, the one for the plus, is much more interesting for me at the point of extending it to higher spin and all that. Well, not because you can get it from the self-dual sector, which you can, but also the fact that it satisfies these BCA relations at any spin. So here it's really saying that I have the double copy of 2 spins, and I just get the generic spin one.
Right.
Yeah.
So, I agree with what you're saying. Yeah. I mean, it's true that all of those massive theories there you can get from the massless theory, and then applying a Kaluza-Klein.
Yeah, and that's the point that Arkani Hamed made in their very first paper of massive amplitudes, which is that these have a nice high energy version, and they are fixed by that.
That's true. That's true. They have very nice high energy.
So they did it kind of in the opposite way by taking the high energy limit, but you can think of it sort of coming from the massless theory already in 10 dimensions, just reduce it.
Yeah. I agree, yeah. I think in paper maybe it could have been more clear in which theories they were talking about, but yeah.
Yeah, well, that's why we wrote a paper after that.
Yeah.
I cannot see more questions coming from you guys, so I think we should thank Henrik once more. And this was our last lecture, right?
Yes. So David will